your name on it. I guess we'll do a raffle and give you a T-shirt. Is that what we'll do?
Yeah, we'll select some lucky winners and send out a T-shirt. But if you're interested in learning more about Hazelcast, feel free to sign in.
Yeah.
We'll select 5 people and give a T-shirt out.
I think we're going to send them out later on. Okay, so thanks so much for coming. And my name is Fuad Malkov. I'm Hazelcast co-founder. I've been with. I guess you guys had Talib here last year. So I don't know how many of you were present. So Talib started Hazelcast, and then a couple of months later I joined him. We did this from his apartment actually for some time, and then things got bigger, so we moved to California, headquartered there. So we're about 75 people right now worldwide. About 2/3 of them are technical people. About half of total is engineer, like product developers. About 1/5 of this group is my team. We are going to customers, helping them to adopt Hazelcast. So we don't necessarily write code that goes to production, but we help our customers. And the rest is other departments within the company. So we're a pretty technical team overall. So for long years we've been just doing Hazelcast. And actually a question to you guys. So how many of you used Hazelcast, know what it is, kind of is familiar with it? Okay, cool. And how many of you have no idea what Hazelcast is? All right, okay, cool. All right. So I guess I can say half and half. So I'll try to give a little bit of introduction about Hazelcast, but the talk itself is not necessarily about Hazelcast. So we've been, again, building Hazelcast, which is an in-memory data grid. So we call it an in-memory data grid. If you're going to ask what that is, so very simply, just imagine a hash map. Okay, so a very plain old hash map, and if let's say you want to have multiple threads access that hash map, put and get, store something and retrieve something, what do you do? Can you use hash map to share data between multiple threads? Can you? Yes? Who says yes? Okay. Who says no? Who says no? No one know? Well, you can't, guys. Hash map is not thread safe. So concurrent. You didn't ask. Well, what you do, you use concurrent, right? Not hash map. So the guys who did Java, they were like, okay, this thing is not concurrent. Remember hash table? There was hash table, which was synchronized but not concurrent, right? It was thread safe but not concurrent. So then Java guys, they implemented concurrent hash map, which was beautiful because now you can have multiple threads, all in parallel, access it. Of course, it's typical interview questions. How you design concurrent hash map, how you make sure those threads don't actually, can work in parallel. But overall, basically, what you do, you slice the concurrent hash map into buckets, right? And each bucket can only be accessed by one thread. So if you have multiple threads who are actually accessing different buckets, then you have concurrency. But when they fall into the same bucket, it kind of behaves like hash table. It's locked, so only one thread at a time can access that bucket. So more buckets you have, more CPUs you have, more concurrency you can have, right? So it's really, really good. Now, another question to you then. So let's say you want to take that hash map, but now share it among multiple JVMs, right? So we started with single thread, multiple threads, and we're talking about multiple JVMs. So what do you do? Question to you.
Yeah, right.
Yeah, there you go, yeah. So you use Hazelcast. So basically, that's what pretty much Hazelcast is. So you say Hazelcast, you start Hazelcast, we'll write some code here, so it will be part of it, you'll be able to see that. And then you say Hazelcast get map. It returns a concurrent map implementation. So interface is the same that you guys have been using for the last 10 years. The same map, put and get. But what's happening is, in the background, that hash map, just like the way concurrent hash map is sharded and one thread has it. So in the same manner, now this hash map is sharded, but each shard is stored on different machine. right? And also backed up on a different machine as well for high availability. But now you have concurrency in the at multi-node level, not just multi-thread level, but multi-node level. And of course, in every node, you can still have multiple threads accessing the same thing. So this way, now you have suddenly multiple machines storing the same hash map. You can access to that same hash map from different JVMs to put and get and etc. So what we call it, Hazelcast, is a distributed implementation of for example. Now, of course, we didn't stop there. We said, well, map is brilliant, right? A lot of people use map. It's kind of the default cache, right? So that's why map is very important. You can use it as a cache, as in a storage. But then we said, okay, there's a queue. Can we have a distributed queue? Why would you need that? Well, of course you need that, right? There's a lot of pop-up scenarios. You guys are probably using or have used, active MQ, rabbit MQ, zero MQ. So they are all great. But the advantage with Hazelcast is you can actually embed that into your application. So it's all Java. You don't necessarily need to start a server, a process, or something else. You can just embed Hazelcast and you have a distributed queue just in your application. Of course, later we added log, sets, list, executor service to do distributed execution of the cluster, semaphore, countdown, latch, atomic number, just you name them. So a topic, distributed topic, it's not necessarily a Java interface, but it's very common, just has Facebook methods, publish and listen. So we implemented that. So basically it became a JVM toolkit where you can do all these things in a distributed way, but the API is derived from the Java collections, right? Or concurrent API, in the case of executor service and log. And then of course, well, we said, all right, Java guys are lucky, a lot of innovation is going over there, but these poor other, language guys, let's give some love to them as well. So we implemented, .NET, C++, Node.js, and we implemented Memcached interface, the protocol. So if you have any other Memcached client, you can just talk to Hazelcast, thinking that it's actually Memcached even. So anyway, that's basically what Hazelcast is. Hope it's a little bit clear. So it's Apache license. Everything that I said is Apache license. There are some enterprise components on top of Hazelcast, but so far everything that I said is open source Apache license. You can just download it from Maven, Gradle, Docker. Just download it from website. Just start using it. Pretty much any developer can start a cluster within 2 minutes of you downloading Hazelcast. So it's really easy to use. You can really start easier, but of course the concepts are a little bit, complicated in the sense that we're talking about distributed nodes, backups, and etc. So it takes a bit of time, but the API is very simple, very easy, and we'll do some coding, and you'll have a feeling of that. So the reason I was telling all about this is, so that's what Hazelcast as a company was doing so far. And about a year ago, a little bit over that, we started thinking about, what else we can do. And we created a project called Hazelcast JET. Now, it's not public yet, so this is my first time doing this talk. We did this, I believe this is third or fourth JET talk. We started about a month ago giving these talks. And now a beta version is available, and we actually have a sign-up sheet. I'll have the link at the very end. So if you guys are interested, kind of to try that, we have a sign-up sheet. We can add you to the beta program. It's still going to be Apache license, open source, but we haven't publicly released it yet. So today's talk is going to be about Hazelcast JET. So again, you'll hopefully hear a little bit about Hazelcast as well, and you're going to have an understanding of that. But it's more about Hazelcast JET. Okay. So now, before I'm going to dive into JET, I want to talk a little bit about Java 8 streams. Now, again, question to you guys. How many of you have used Java 8 stream API? Wow, awesome. Okay. You guys are probably better on this than me. Again, I'm a lazy guy these days. I don't write a code that goes to production. So it's just me trying to learn on my own. So help me out. So we're going to do a a code right now, okay? So first we want to experience how the world was when there wasn't any Java 8. You know, historical times, you know, there was a guy talking about like when dinosaurs were walking around the world. So that's the same time. So what we want to do is, we want to do, and so I have here old, okay, so to make sure that this thing is going to work, I did implement something, but I'm going to hide this. Okay, so let's write it from scratch. Okay, so this resolution is low. Let me change this. This one. All right, much better, right? So first of all, I have a utility class here. So if you look into all this computation stuff, the hello world of computation is what? Who can tell me what it is? The hello world of any complex distributed example. Word count, right? Yeah. So we're gonna do word count. So surprise. So what I have here is a War and Peace in English. It's just a text file. And what we want to do is, pre-Java 8, we want to write a program that that is going to just load it and find the count of words and extract it to a map. The keys are word, the value is the count. Okay, and we'll have some filters. Let's say we'll do words that are larger than 3. I have a couple of special words. We want to exclude them, like this is that kind of things. And what else are we going to do? We're going to lowercase them, just make them, unified and etc. Let me do this. Okay. So first of all, I have this. I have this word util, okay, that given a file name and given a map, it can load the file into that map. With key being the line number and the value being the file, okay? And then I have another method that's called clean word, which basically will replace, everything that's not like normal character with empty to make things a little bit easier. Okay, so what we do is basically first we create a source map, okay? So this is going to be our source map, and this is going to be a hash map. As I said, it's going to be integer and string, right? No, the first we're going to load, this is the source. So keys are going to be the line numbers. The value is going to be the string, right? So that's going to be our source. And then we're going to have a destination as well. Let's call it and that's going to be string and integer. And let's call it count map, and this is another hash map, okay? And then how do we load this? We basically just do word util that fill map with data. The map name is war and peace png.txt, and our source file is this map, right? So hopefully this is going to load it. It's going to throw an exception. That's fine. Then once it is filled with this source map, then what we need to do, right? We need to somehow count all this thing, right? What we need to do. So I actually have this in slides. So pre-Java 8, the stuff that we have, collections, iterators, for loops, if-else, ugly stuff, right? So we don't like them anymore. Suddenly we just, get more smart. So, but let's use them. So what we do, so we typically can do for each string, let's say a line in the source, in the source map values, right? I can do that. So for each line, I can do string tokens equal to, I have a pattern here that I've defined before, that split this line, right? So I suddenly have the tokens, So for each token now, what I want to do is, I'm going to take the index length. So for each token, I want to do, first I want to lowercase that, right? Tokens e to lowercase, and then, oops, this is string my word, and then I want to do this clean word thing. I want to just clean it up. Actually, do it over here. Word. Okay. So I lowercase that. I cleaned it up. Now, what I need to do is, now I need to store it on my count map, right? So what I can do is count map. I can do like put if absent. You know, like first time. The key is going to be the word, the value is going to be 1, right? But if this guy, let's say, if this guy, so if it is successful, put if absent, meaning that there wasn't anything else there, it's going to return me a null, right? So we'll put 1 there and we'll return me a null. But if it's already something in there, I don't necessarily want to replace it with 1, so I'm gonna actually, if it is not null, right, which means that I couldn't actually store it in there, so I'm gonna do count map.get the word, I'm gonna get the count, and then I'm gonna put it back by doing word with plus count. Does that make sense? Okay, so I'll potentially have this, right? Then we can do actually one more thing here. I want to only store words if word of length is greater than 3, okay? Okay. So we store everything that is cleaned up, lowercase, words that are larger than 3. Oh yeah, one more thing. We had this, I had this thing, word util. I had exclude, so let's exclude the words here. So word length is greater than 3. I want to do excludes, I'll do that, you see? I had a cheat sheet here. No, I don't have it. Okay, so let's exclude them. So we don't want word. I guess we can do.
Can you explain put if absent? I've never used that, never heard of it.
Yeah, put if absent is a. Put if absent basically is kind of like an atomic put method. It will only succeed if that entry is not there.
And it's on Java util hash map.
Yes? Java util map. Yeah, hash map. Yeah. Yeah. But it's the same, right? I mean, I could have wrote that as, client map.get. If it is null, then put 1. If it's not null, put, +1. I like this better. So one more thing we need to do here. If word length is greater than 3, and then for each string, what's my name here? Exclude inside the excludes. This is just an array list. If word.
Why don't you just use paint?
That's on the list though, right?
You said it was an array list.
Say it again.
If excludes is an array list, as opposed to an array. Is an array still a list or is it an array?
It's an array. Okay, so list collections as
Arrays as list.
where it says list, what is that? Excludes, contains my word, right? So
Okay, so-
we don't want this to be, if word length is greater than 3 and doesn't exclude this. Now this is going to be ugly, of course. What we're going to do here, we're going to just actually convert this. There's my excludes. I'm not change that, but I'm going to put it here. This stuff, string excludes equal to this thing.
Sorry to bang on about this. Put if absent is Java 8. This was, you said this was pre-Java 8.
I believe that's actually, it's actually not Java 8.
No, it's not Java.
It's not Java 8.
But the API for 1.7 doesn't have it.
Yeah, I think it was added in there. I think they added this in 1.8.
Okay, all right.
Yeah, it was added in 1.8.
Okay, concurrent hashing method. I'm sorry. Okay. Yeah, concurrent hash method is there. That's yeah. Let's make it concurrent hash method. Okay. My bad. Yeah, it's hard when you present to smart people. Okay. Now let me prove you. Now
Not smart, just always two releases behind the times.
Okay. All right.
If we're fixing stuff, your war and peace is misspelled too. The file name something.
Yeah.
Peace is misspelled.
That's
Okay. All right. So we have our source map, right? I expect it's correct. So what I need to do now is let's just print. Let's find the top 20, right? Can we do that? Or let's not do that. Just let's print the size of our final result, right? How many words we found. I mean, we could have printed everything, but let's just do this. Our count map size. Okay, let's just see how many we have. We can have our source map size as well here. This is going to be and technically the interface is concurrent map. So if you go to concurrent map 1.5, it has the method with the absent, okay? Since, does it say here? It doesn't.
It was in place.
It is in 1.5, yeah. Okay, so they added default apparently to the hash map with Java 8. Okay, so let's run this. Our source map is right here. Let's print that as well, right? Just our source is okay. This is our result. Okay, let's see. Oops. That's the other code that I was going to write. So that. Okay, good. Another code. Can we there? Two. Okay. More time. Okay, good. So the source, we had 65,000 lines, and when we count every word, when we reduce to the word, we ended up with 17,020 words in total, interesting words. And of course, they have numbers. We could have sorted that, and etc. But it's just easier to sort that with Java 8, so I'm going to do that over there. But anyway, so this is the code, right? We have for loop, we iterate through that. We have all that stuff. So that's really boring once you start to know. Once you start to know. So we just did that with Java 8. So I got this from Jerry Abel website, really great cheat sheet. So hopefully it's okay. So what is Java 8 Streams? Basically, what does that give to you, right? So Java 8 Streams is not a data structure, right? So it's just a functions, and it's kind of like if you guys know Spark, it's like RDD. The Spark guys introduced the concept of RDD. So it's the same thing. It's not mutable. So what happens is, as the data comes, you can move the data to a different map, to different sources, and apply some functions and transform it as it goes. But it's technically not a data structure. Doesn't take data. You have like cool methods like map, flat map. You can filter it through there, sort it, distinct it. Do for each. A couple of examples. We're going to of course write one of these. So it's definitely a much different style of coding than what we used to do. And actually, as you write all these methods, until you call this reduce method, actually none of these do execute. So they don't execute until you call reduce. Only then, it starts to map it, filter it, map it, filter it. And the same here. The collect is the I think it's called terminal operation. Yeah. Collect is terminal operation. Unless you call it, nothing is actually executed until that time. So basically, like if you stop here, that is just a definition of what you want to do. It's not what you actually ask to do. It's just that you just define what you want to do. And when you call a terminal operation, Java then it starts to actually evaluate it and process it. So it's kind of a little bit interesting. So let's write our code in Java 8. Hopefully you guys can help me out on this. All right. Come on, I don't want to show this. Okay, all right. Let's copy our source code from here. We had these things already. Fill the map, print it out. Fine. And the exception. Okay, so we have the start, the same start. Now what we want to do is we want to do a source map, right? Dot entries, entry set dot stream, right? This is how you get the stream. So you have to have a collection to get the stream. Map itself is not a collection, so we could have done values as well. Let's probably. Let's skip the entry set. So once you have that, so the first thing we want to do is we want to map this to the log. No, we want to tokenize this, right? So we want to do a flat map, right? Do you guys know the difference between map and flat map? Who can say what's the difference between a map and flat map in Java 8 Streams? Okay, so a map is, go ahead.
Map is one-to-one, and flat map can be multiple.
One to many, yeah, exactly. So let's say, what we have is first a line, right, which is, our first map is every entry is one line, right? Now, if we want to, let's say, for example, make every word there uppercase, right? So basically we have n number of entries here, and want to map it to another map which is n numbers, then we can use map. It's going to just one-to-one map. But if we want to take this and actually create more entries from that, like one to many, then we use flat. Okay. It took me for a while to understand the difference. So right now what we want to do is every line has multiple words, so we want to flat it to every word. Okay. So the flat map, and basically what you do is, you know, the first argument is your line. This is my line, right? And then what I do pattern. There's actually split. So you basically return a stream of values, okay? So flat map, into flat map, you need to enter a function that will return a stream of values, okay? So what is our function? Our function is this pattern.split, right? So we want to take each line, L represents a line. You can give any variable you want. But since it's a string, it understands that, you know, those entry set, sorry, L actually is an entry set. It's not the line, it's not the value yet. So it's entry set. So what we want to do is we want to take the value of that entry set, right, which is the line now, and do split. And it's going to return us another stream of values. And then when you do flat map, now technically at this point, I wrote a definition of how to convert this map to a different map. Nothing is executed yet, but the definition basically now is completely different map, right?
So why didn't you start with value?
I could have, but I just thought that I might use the key later on. Well, I can actually. I can. Let's do that. I don't need the key. Yeah, you're right. Let's say, but for some, you know, on a different application, you might need a key, so you can preserve that. Now, you know, let's call it a line. Now we know it's a line directly, so I can just do this, right?
You can also just do a method reference.
Yes, you can probably do that as well. Right? Yes. So it's a kind of different way of saying the same thing. Right now we just say, okay, this is the function, and it understands that, you know, there's one parameter coming out of this, you know, coming into the flat map, and this function also takes one parameter, so it just applies them. I mean, you don't necessarily have to exactly call it, so we just give the function for it to use. Yeah, good catch. And then what else we want to do? Now the flat, now this created us a stream of, you know, all the words, right? So what we want to do is we want to probably lowercase that, right? Then now we want to do map, and we want to do that string that lowercase, yeah, to lowercase. So I want to do that, and then let me cheat now. What else we'll do? Yeah, we can clean it up, right? So basically, now we are just transforming every word that we have, right? We want to do this clean word thing. I'm going to do what's word util. Clean words, so I'm cleaning it up. Let's say we want to do filter with all the words that's length is, you know, L does. Length is greater than 3, right? We want to filter that. And I can filter with excludes dot contains now this is now words. Words. Now this word. Oops. Contains word, not contains, right? No, sorry. Okay. All right. What else do we want to do?
What's that last one doing?
Say it again.
Can you, what is the last one doing?
Sorry, yeah. So remember we had 3 criteria we were doing, right? One of them, every word needs to be at least 3 characters long, more than 3, and then not contain any of these words that we have, you know, like some typical words that are not interesting. So I'm kind of limiting them as well. We had the same in the previous code too. Let me see what else we do here. Yeah, the final is we're just going to collect them. And so now we have the terminal operation. So the collect, we can do a, you know, they already provide us some good collectors. So we can convert this to a map. Now to map, first we need to define what a key is, okay? So the key is, it's going to be, let me see. we're going to use the same word we're going to use as a key, okay? And then, let me see if I can get this right. So the same word that we've been, so far transforming, that's going to be our key. Now the second parameter says what is going to be the value map, okay? So initially our value is going to be 1. Kind of remember, like you put if absent 1. So the first value we want to do is 1. Now, of course, as this guy is collecting these things, let's say there's a word, there's a word called princess, for example. So the first time it sees princess, it will say, okay, this is a new thing. So how do I convert this to a map? So it will take the princess, use it as a key. The value will store as 1. And then this parameter now asks me merge function, which says, I think this should be, yeah. And then the last parameter says, okay, if I have now the same word again, how do I combine them, right? How do we combine this? We want to add them, right? So we start 1 at the beginning, and if there's another one, right, we want to add 1 to that, right? So we're just going to do integer sum. All right. So so this potentially should give us this guy. Count that. And I think I need to do what am I missing, guys, here? We have the cheat sheet here, right? Let's have a look.
Is it just in your types wrong?
Yeah, somewhere, but
It should be a map.
It should be a map, not a hash map. You don't know what you're getting back. It's a hash map.
yeah, but I have defined it as a map here.
Yeah, but in
Up
your,
above,
Oh,
yeah.
yeah, this is
not
the same.
right.
This is not a hash map. Yeah,
Yeah,
you're right.
this is a map, right.
Yeah, that's right. There you go. There you go. Okay. Cool. So now we have our count map, right? So now what we can do is, this we can print the size, right? Count. We can have that size, right? And see if we get the same value. I think it was 17,020. Okay, good. So far so good. So now, but of course, with streams you can do much better stuff here. When we have stream, I can do count map dot, sort. I think I can do count map dot entry set dot sort dot stream dot sorted. I can give a comparator here. Our comparator is going to look like. Slightly complex. We need to define how to sort this thing. Or I can do this actually, let me see.
If the received parameters in entry is E, then you should be able to just get the value out of it. I mean, the key out.
Yeah. But what we want to do is we want to sort based on the value, right? The key is the word. Yeah, the value is the count. So I need to provide a comparator, which is basically going to look like this. It's going to say,
You don't need a real comparator because it's a functional interface. All you need to do is write that.
yeah, we just need to write that down. So what I need to do, let me see, I think I have a cheat sheet here. So if I have these as a, so I just need to go to dot get value minus the one dot get value.
You should actually do compare. You should not have to know about minus and integers and rollovers and all that fun stuff.
Okay.
You just take whichever value you want.
So dot compare to, okay. Makes sense. Is that ascending word or descending word now?
What was the question?
Descend, right?
Two.
Okay, so this sorted map should give us another map, right?
No, just give you a stream of that.
Sorry, stream of, yeah. So and then what we can do is we can limit this, right? What I can do, I can, now I can limit, let's say, I can limit this, let's say, to the top 10, right? And then for each of them, I can do this. Okay. Hopefully I got it right. Yes, looks like it's right. Okay.
They was not in your exclusion?
Say it again, please. They, I guess it wasn't. Let me see. Yeah, it wasn't.
It's not.
Yeah.
Cool.
Okay, all right. Good one, good one. Okay, so far it's all Java 8. It has nothing to do with Hazelcast, right? Now the fun part is this one. So,
I have a question.
yes.
Can you just comment on the runtime performance of the old style and the new?
Say it again, please. Sorry.
Have you got a comment on the runtime, the speed of the two?
Of the two? No, I haven't, but you actually reminded me a good thing. So here's what you can do very easily. So you can just take this count map and do parallel stream. And then everything that's been done is going to be in parallel, done in parallel. Like, all the, take each line, convert them, merge them, etc. Now, on the old code, you had to manage all that yourself, executor service, submit this, make sure they all correct, nightmare. This one is beautiful, actually, I haven't seen which one's faster. I assume this one is going to be.
It's not that beautiful.
Here's why. Parallel stream uses a single tiny thread pool. So if it's running all by itself, it runs, I think, 5 threads or something like that. But when you start having parallel requests coming in from web servers and you're doing this, you can actually have that run slower because it can't get any threads because they're all being used by different requests through the parallel stream. Because it's this, all parallel streams use a
It's going to use the
single
same thread. Okay.
That's not configurable.
Well, it is, but suddenly that nice little line turns into like this much code
Because you have
to override, to give it its own custom thread pool.
All right. Yeah. Good point. There you go.
Good demo. Good demo.
But yeah, it works in the demo, right?
It does. It always works.
Yeah, but I guess you can hide some of these configurations maybe, or
I'm just wondering if you catted your text file 100 times together, make your text file 100 times bigger. Because you can't see it when it's milliseconds of difference. But if you had a big enough data set and your input was big, 5 minutes is a lot worse than 1 minute. I just wonder what the runtime
no, I haven't
difference
done
might
it.
be.
I haven't
Pick
done
a one.
it. But I assume again, all the side effects in real life putting aside, this one with parallel stream definitely will be faster. It's going to use all the CPUs here, where the other one, was just sequential on a larger one. But no, I haven't done performance honestly. Okay. Now let's do something else. Let's take this code as is. Let's see if we're gonna, first let me actually introduce you to a couple of things. So now what this talk is about actually, the JET, right? So, you know, I talked a little bit about Hazelcast. I'm gonna show the code of Hazelcast as well, but very 2 slides of introduction here. So, you know, I mentioned what Hazelcast is and what we can do with Hazelcast, right? One of the things Hazelcast is kind of unique, I would say, given, you know, like other caching solutions, you know, like compared to Redis or, you know, NoSQL databases. You know, we are pure Java, single jar file. So just like, you know, I was adding a hash map into my, you know, you know, I was importing a hash map and or concurrent hash map and using that, you can do the same thing. So just include Hazelcast into your project, you know, import it and then start using it. So, and suddenly all the JVMs, you know, using Hazelcast, they're going to discover each other. Default uses multicast, so it really works on a, you know, on simple networks. But if multicast is not enabled, we can use TCP/IP configuration, and we can provide the IPs of the machines to discover each other. If you're running on cloud, for pretty much all the providers, there's their own discoveries that you can configure without writing any IP addresses down there. You know, Hazelcast nodes can find each other. But long story short, at the end of the day, you know, all these JVMs are going to be communicating with each other, okay? And it uses TCP/IP. The discovery part can use other stuff, but after everything is discovered, everything goes through TCP/IP. So when you did put something, right, Hazelcast will determine on which node it needs to store that entry. It will serialize it, send it to that node, it will store it there. But from user, from the application, all you are actually interacting with is the Java API. And that API is the same as, you know, mostly as the Java standard interface, so mapped in this case. And Hazelcast node will be living in this JVM. Now this has advantages and disadvantages, yes?
So is the entries, are they spread out?
Yes.
Or are they replicated?
No, they are spread out. Good question. So this is a partition implementation. So it's not a replicated implementation. They are spread out. And again, you know, because this is not a Hazelcast talk, I'm not going into very details of that. But what we are typically doing is, let's say, in a 3-node cluster, just for simplicity, let's say we have 3 million entries to store. So million is going to be stored here, million is here, and million is here. Now, we want this to be also high available because everything is stored in memory. So Hazelcast is all about memory. And if you want to let's say if this node goes down, you know, it could be a failure, or it could be, you know, you're restarting a node because either you're upgrading something or, you know, it's a managed process. And you don't want to lose data. So by default, every entry has 2 copies. So we call it one primary and the other one backup. So basically one backup. So what we will do again, 1 million is equally distributed to each other. And then all the entries here, the million entries here, half of them are going to be backed up on this node and the other half on this node. So the same goes for every other node. So technically each of them is going to be storing 2 million entries. But overall, you have 3 million entries. And if any node goes down, you are not going to lose any data. Again, you know, yeah.
I know that we weren't going to get too deep into this, because when you go away from the multicast discovery, do they teach each other so that you can have clusters that only know about things in one direction and they teach each other?
So for discovery purposes, yes. What I mean is that, let's say, you can have another JVM that only knows this guy, okay? And if I can connect to this guy, he will basically introduce me to the rest of the guys so I can join the cluster. But like if you have only, I don't know, I mean, I can only talk to this one, and I can never talk to that guy. And if I can just kind of use this as a proxy, not really. So we have like Java clients, and we call some of them dummy, meaning that they only connect to one guy. So you can kind of work around that scenario. But the nodes of the cluster all of them need to be talking to each other. But for discovery purposes, it's kind of like, you know, if I want to come to this meeting, I need only to know one guy who can give me the address of the meeting. And as long as he's in to get me in, I'm fine. So, yeah. So, and now in addition to that, this has advantages, you know, it simplifies a lot of things, but disadvantages are, who can tell me? Who can tell me?
This model.
Yes.
Well, you're not getting much of the advantage of moving it to a separate JVM, right? You're still in the same JVM.
You're going into the same JVM, you're exactly the same JVM.
Well, that seems like that's the disadvantage. At least. That seems to me like that's the disadvantage. You want to, I mean, the whole point of an in-memory database is out of the same JVM. I mean, I can do this without Hazelcast. Right?
How can you do that without Hazelcast?
Well, then, I mean, because I can use a concurrent hash map and just send messages myself, right? So the whole point is to have something that's
Right, but then you have to invent all this, you know, this
well,
the
just
backups.
just the sync, yeah. Right.
Yeah, but yeah, trust me, it's much more complicated than that.
Right.
Yeah,
These were
but yeah, disadvantage. Yeah.
This one is. Well,
No, no,
they'll
no,
say
no,
that
no,
they're
it's
sharing
one of
in
those
the sharing in the original JVM. Though.
Oh, right, but each one of these is a separate box.
Yeah. No, I get that, but the Hazelcast nodes are part of the original JVM. To me, one.
No, it's you know, to some degree it's an advantage because you don't necessarily have, like, let's say you had an application, okay, that, you know, I don't know, let's say Disney and you have some registration application. Let's say, you know, the customers comes in, they log in, so you create a session for them and, you know, and you keep that session in Hazelcast. So before Hazelcast era, let's say, you had a sticky session and you were storing them on a concurrent hash map, kind of like you said. You know, sticky session, whichever machine, you know, you land in, you always hit the same machine, so you don't necessarily need Hazelcast for that. But of course, then, you know, you have really not equal JVMs, and if suddenly, maybe not for Disney, but like if, you know, for some other use cases where one customer is really, you know, hitting a lot compared to the other, so whichever machine it hits, you know, it creates the hot request there. Or, you know, if that node goes down, the session is gone, so you have to kind of deal with that. So what you can do is, without really introducing anything else to your application, you can put Hazelcast in there, right? And start to store, instead of concurrent hash map, into Hazelcast, deploy this, and suddenly, again, without your operations guy really knowing what's going on in terms of, you know, now you have to start these processes in these machines, you don't tell them that. And suddenly you have high available sessions, for example. So that's good. Works really well for a lot of product companies, you know, that sell, like we have a lot of customers like, you know, Cisco, you know, HP, have some monitoring, you know, applications for the other stuff that they sell. And then, you know, they suddenly, they call it modernizing their applications, making them high available and etc. And they introduce Hazelcast, you know, they don't really need to add a lot of changes into their deployment. But disadvantage is, as the data grows, now suddenly you are sharing the heap with Hazelcast, which suddenly stores gigabytes of data in there. You know, say you want to store a lot of data and it shares there. And then, you know, you get out of memory. So is that Hazelcast or is that you? And even if that's you, one of the nodes goes down. Now you have to deal with Hazelcast rebalancing or recovering that data, which is not necessarily cheap. You know, if the data is not here, I have to recover from the backup, I have to reassign a new backup and, you know, copy some of the data. So it's a lot of work to do. And some of the, and also sometimes, you know, like some teams have more frequent deployments of their own application, and it doesn't necessarily need to be depending on Hazelcast, right? So you want to be able to deploy your application independent from Hazelcast, kind of like the old client server model works really well for those scenarios. So we have that as well. So, you know, you can have, now we call it Hazelcast Client API. It's the exact same Java API, uses the same interfaces. You don't need to do any code change. Well, only one line code change. But the API is exact same, behavior is exact same. But now you have Hazelcast nodes on a separate JVM. So basically you can kind of do what you want to do. So this is kind of like what Hazelcast is in terms of deployment model. And you know, just a little bit of, you know, why people use Hazelcast. Again, it's about in-memory, so really fast data storage. It's designed to be distributed from day one. Like a lot of, you know, other solutions out there, they've added sharding or, you know, this scalability later on. You know, they design, like think of MongoDB even, for example. They had, the very first, they had this replica sets, that's how they were scaling. And then they introduced this sharding, and it was kind of later on added to the product. Whereas Hazelcast, from day one, we designed this to be distributed. So, and we were telling people, if you're going to use Hazelcast on a single node, don't use that. Go use Guava Cache, EH Cache, something else. Something that is designed for local JVM, JVMs. Because whatever you, even if on a single node, when you do Hazelcast we're going to serialize that. Because we'll assume that, sooner or later you're going to have another node that will require that. So, I'd rather keep it in a serialized format so that, when someone else asks for it, I can just copy and send it across the network and not worry about serialization at that point. So those are the things that we have. So scale-out computing really works, from day one. When you add a node on the fly, Hazelcast will take care of it. So you don't need to worry about restarting everything when you're introducing when you want to increase or decrease your capacity or anything like that. So it works really well. Programming model, I kind of talked about it a little bit. The API is very simple. You guys all Java developers should know about that. Yeah, resiliency, automatically there's backup, so you just kill a node, we recover the data, you don't see anything. Yep.
So resiliency only works if there's other nodes that are constantly running, right?
That is correct. So yeah, it's not
There's
no
storage of any sort.
Now in enterprise Hazelcast version, we do have a disk persistency, and that's only designed for, we don't call it persistency, we call it hot restart. So it's kind of designed for when you have hundreds of gigabytes of data, and somehow you want to restart your entire cluster. Now typically what you do, you have that data also stored on a database or something like that, and you can reload it. But there are customers or users that this reloading process takes 24 hours. Just reading that information from database. So what we do, as you go, we dump everything into the file system, and manually, this is a manual operation. You know that you're going to restart everything, so you kind of put Hazelcast into froze mode where it doesn't migrate any data, and then you restart everything, so it basically just shuts itself and comes up with in the state that you left it. But apart from that, you are basically resilient to the number of backups you have. So if you have 2 backups and on a 10-node cluster, and if you lose 2 nodes at the same time, that means some of the data will be both primary and backup on those 2 nodes, so you're going to lose it. Now, if you think that data is more important, you can have different maps with different backup counts. But that's kind of like a trade-off, right? I mean, you can't have, this resiliency and these at the same time. So you can kind of have some window there. Yeah.
I have a question.
Yeah.
So I think I understand. You have key value pairs that could leave one VM and move to another one. So what do you use for serialization on the wire?
So we require whatever you store in Hazelcast, that thing needs to be serialized. So you can, by default, just implement serializable interface from Java. It's enough, but it's not the best way. It's slower to serialize and also generates too much byte output. We have our own interfaces, like externalizable, where you can implement will be much more efficient. Some of them even have versioning support, so you can have like different versions of the same object in the cluster, and we can read and write from different versions to each other. And finally, we have pluggable serialization. So there's a lot of examples how you can do it with Cryo, with with JSON serialization, for example, if you want to do. So basically, you can actually plug and tell Hazelcast how to serialize certain things. But from Hazelcast perspective, if it is primitives, we do serialize them in the most efficient way. But if it's a complex object, you need to make sure it's serialized. That's kind of where you need to know that this is Hazelcast, not just your Java hash map, because we don't in a hash map when you store something, it's stored by reference. In Hazelcast, it's going to be stored by value. So we're going to copy that, serialize that, and then store the value, not the reference. So that's the only differentiation, actually, where you can break the same code that runs on Java hash map that doesn't run on Hazelcast, because we assume it's by value. But 99% of the time, users really get it, so it's not a big deal. 1% of the time, sometimes we get people that saying that, hey, this is wrong. Yeah, there's no way around it. Is that clear? Did I answer the question? Or was that?
You answered my question about, I had a feeling you might default to serializable. But then what you were talking about by reference and by value got more interesting.
Okay.
Can you explain that again?
Okay, sure. So when you have a hash map, let's say you have a customer object, okay? And you store it in a hash map. And here's the code. You say map.get, right? It returns a customer. And dot, let's say it has a set email method, for example. Set email, something new. And then on a different thread, you say map.get, get email. You will see the updated value, right? Of course, assuming that it's volatile layer, etc. But eventually you'll get the updated value. Now, with Hazelcast though, when you do get customer, right, get entry, it gives you a copy of the customer object. And when you change it, you've only changed the copy that you have. If you want to put it back to the Hazelcast, you have to explicitly call map.put_back so that another thread, when it goes and does a get, it will see the updated value. You see what I mean? So in HashMap, you don't have to put it back because what you got from map is the same reference to the same object. So once you change that object, the content of that object, map content changes as well. Whereas in Hazel, it's like database. I mean, you do a select from database, you get a record set. Whatever you change there, you just change your copy. When you have to, hybrid net probably can does that for you in a better way, but you kind of have to have some way of putting it back. Now, back in days, Terracotta used to do bytecode manipulation, so you were still dealing with map, the way that you would do Java, but actually they would change the bytecode for you, and that would actually synchronize it back. But that was problematic because, let's say you have 10 fields there and you want to update 10 fields, they would do 10 times store back to the grid. And that would be, not efficient. So what they ended up doing is they acquired the Hcache, they put the Hcache as their interface, became more like Hazelcast, and then it was more clear what you can do and how you can do it. So there's no really workaround to that problem. Or difference, it's not problem, difference from Java. Okay guys, so I want to go slightly, okay, so this is the basically all the features that Hazelcast have. The darker ones are enterprise features, but everything else in the core is open source. We have again Healthy Start Store. We have off-heap capability, that's enterprise. The same off-heap capability as on the some of the data structures, so you can have option for those data structures. But all the core is open source, and I don't know, we have tens of thousands of users. Okay, so now Hazelcast JET. I know it's been almost an hour, but kind of the crowd also was new to Hazelcast, so I enjoyed that part as well. So what Hazelcast JET is? Remember I was talking about how you can include Hazelcast in your JVM. So it's kind of like a separate project that includes Hazelcast. Now this is of course our project, but there are other projects like that already. Like if you look into MuleSoft, WSO2, Apache Shiro, Vertex, they all include actually Hazelcast in their JVM for some reasons like clustering, message queues like in case of MuleSoft, WSO2 uses a cache. So people do use Hazelcast for the same things, and JET in a similar manner. But what a JET is, it's a direct acyclic graph computation engine. So we call it DAG engine. It's basically a way of processing data, in a acyclic graph. So Spark is also like DAG engine. So Flink is a DAG engine. So it's kind of like a more generalized concept than MapReduce. So when MapReduce first came out, you had to write mappers and reducers, right? And then people thought about it, and then they said, you know what? It's actually a specific case of a direct acyclic graph processing. So you have these vertices, and you do some processing, and then you do another processing, and then you transform it, and basically map and reduce is a version of the DAG engine. So I think the Hortonworks guys, they created something else called, I forgot the name. It was more low level than, let's say, Spark, That was also DAG engine. So Hazelcast is another DAG engine basically. But the idea, the reason we have created this is because, I talked about hash maps and how we are actually native to the Java. We use the same interfaces, we do the same things. So what we did with this is we said, okay, let's create this engine, and I'm going to show you the low-level API as well. It has this DAG API where you can literally say, create these vertexes, and then you link them, and then, as data comes, it starts to process this one, and then it sends over here, etc., etc. But we said, let's put the Java 8 Stream API on top of this, okay? And this way, just like what we did with Hazelcast, now let's take it, because Java 8 Stream API, again, is very similar to Spark RDB, or it is like a, kind of the, like every line that we had, map this, map that, flat map. Those are like vertexes, like those are the transformations that you want to do, and by that, you are actually linking them to each other, right? So it's the same thing. So you define a DAG like this, so you start here, you filter it out, you do a, lowercase and etc. And when you run a terminal operation, it starts to execute, right? So we put the Hazelcast API on top of it. So what I am going to do now, show you, how you can do this thing with JET. Now, it took us a lot of time to write the code, so let's just read this time. Let me just put it this way. Okay, so I talked about how you can start Hazelcast, right? So the first two lines, actually we can just have one line for now, and I'll show kind of what the other line means. So the first line is we start Hazelcast inside this JVM, okay? Now, to use JET, you don't necessarily need to do that, but in this example, what we're going to use is, we're going to use JET to read from a Hazelcast map, okay? Process it, transform it, and to write to a different Hazelcast map. Now, this is not the only way for JET to work. JET can read from, Hadoop, HDFS, can read from, other sources, and can write to the other sources. But again, this example, the first thing we did, of course, is to integrate that with Hazelcast. So in this case, what we do is we create now, see how you create a map. So instead of doing a new concurrent hash map, what we do, we say, this Hazelcast, give me a map, and we give a name. Now in a different JVM, whenever you reference to that source map, it's going to be giving you kind of pointer, a reference to the same distributed map, okay? So this way you can share the data. That's it. Those two lines of code is enough for you to start Hazelcast. Now if you press run twice, basically run two JVMs in your machine, they're going to form a cluster, and like you can do a put on one from one and do a get from the other one, and kind of show. Now for this example though, here's what we do. So this is the JET where we actually wrap this map with iStream map. Okay, so they're going to be like some other wrappers as well for HDFS and other stuff. But for this one, we have iStream map. Now, of course, since Hazelcast map does implement the Java hash map, you can do map.stream there as well, like map.entries.stream. But why it doesn't work? Who can tell me why it's not going to work? I mean, it could work, but since we haven't implemented, so Hazelcast doesn't reference, does not depend on JET. So that's why Hazelcast itself doesn't have distributed string capability. So when you do entries, it's going to actually just do entries, collect through all the JVMs to that machine. Probably that machine is going to go out of memory, but it's going to do that. That's what the API does. And then you basically call it stream on a local copy of a collection. So that doesn't work. That's why, and in Hazelcast, we do not depend on any other library. So that's why we kind of need to have this wrapper to get to that state. JET, though, it already depends on Hazelcast, so it's kind of easier. again, so what we do, we take that map, we wrap it with a stream map. Now on top of stream map, so when you do dot stream, now you have the distributed stream piece. Now on that distributed stream, you can see the same method, right? You can do flat map, okay? And this is what you do inside the flat map. Now you can do a map, you can do another map, you can do a filter, you can do collect, right? Now, the only difference here is all these methods that you are passing, right? They need to be, like the functions, the lambda functions that we are passing, they need to be serializable for the JET to work, right? Because what happens is we're actually sending these code to the nodes where the data is, transform it data, because we want this to be parallel executed, right? Just like parallel stream, where stream was single threaded, you did parallel stream, now you're doing on multiple threads. Now you do this distributed stream, sort of. Now you are actually executing everything on multiple JVMs. But these things needs to be serializable. So what we've done is, these methods actually have, extended methods with, let's say, if it takes a comparable, we've defined a distributed comparable that actually implements serializable. So the code looks nice, but if you click on a map, you'll see it actually accepts distributed, mapper or whatever these things require. And to that, there's also a collector that we have provided. So instead of doing collect to map, which will collect it to a, just a hash map, what we want here is collect to IMAP. So IMAP is a Hazelcast. I stands for Hazelcast, but the rest is the same. And then let's say we want to do a sort here. So we do exactly the same sorting. C sorted. This needs to be distributed comparator, not the normal one. We can collect a different map here, and this one I guess I'm doing a. So once I limit to 20, I convert the result into a different map, and then on that map though, so this part is local. So when I call entry set on a map, that's just going to give me, local list, local entry set. And then this stream, this thing is just local. It's going to print the value. But anyways, in short, it's the same code, right? Pretty much. I mean, there are changes that we had to do in one or two places, but it's the same code that we've implemented before. And when you run it. So this is where it starts Hazelcast. So that's kind of like the Hazelcast starting point. So we have one JVM, one member of Hazelcast running in this JVM, and this is the entries, the values. There's some debuggers here, and then we print the top 20 here. It's not sorted. No, I guess that didn't work. No, this is not sorted.
Sorted.
Yeah. So it was sorted, but when you print, it did not print in the sorted order.
Yeah, put it back in the map, which is
Yeah. Okay. Good. So if we have this line, then you can actually start a cluster of Hazelcast nodes in the same GPU. So there are going to be 2 nodes, and you can actually call one of them shut down, and the other one run. Okay. So one node started, the second node started, they formed a cluster. This is kind of the first node printing the members, and this is the second node printing the members. So you see the double line of the results will be the same. But of course, in the background, now the data is parallel, the distribution are parallel. So that's basically what we are working on, and now I'll quickly show you a couple of more things, and hopefully we'll be done.
Before you
Yeah.
leave that space,
Yeah.
the filtering isn't occurring on the individual nodes.
Yes. Yes.
So how is the code getting over to the other nodes?
So it's a distributed stream, requires distributed predicate. That's the Hazelcast overloaded part. So this lambda is cast to a lambda that is serializable. So basically it kind of becomes as if you add a Java serializable interface to this lambda function. And then in compile time, this is added by Java. And so basically that lambda is a serializable lambda. Because you're using our API.
I don't know what a serializable lambda is.
There's no anything called serializable lambda.
What does it mean to serialize code, I guess is the question, right?
That's
At
the
least
question. Okay,
that's
all right,
the-
all right.
We're not used to doing that, right?
Okay, good. All right. So imagine this is the Java is a function predicate, right? This is normally what Java stream filter method requires you to know. So what we did as a Hazelcast, we have extended that. So we said, okay, we're going to create something called distributed predicate, okay? And this is the interface. Now this is going to extend this predicate, which is perfectly fine. In addition to that, it's going to also be serializable. So we define this in the runtime. So now when a method wants this instead of that one, and when you provide a lambda function that satisfies this, Java will be able to serialize that class. A lambda function is basically class mode, right? I mean, it's an instance of, it's an instance of this.
Right, but a functional interface is just that, it's just an interface.
Yes, but at the end of the day, what you do is, by providing a lambda, you actually create an anonymous class that implements that interface, right? Which is also implements a serializable. So
Yes, but class implements a serializable does not transfer the code.
Normally you don't set the code, right? You just.
we don't set the. Oh, sorry.
It's gotta be set-
Sorry.
it's gotta be set
I
in
got your
function.
question.
That's
I
the
got your
code.
question.
Yeah.
Okay. Okay, I got your question. So this code right now, because I'm running in the same JVM, this code is already my class mode. So when I actually serialize and send it, let's say, across a network, I mean, it's the same as JVM, right? Over there, when I deserialize it to the object, I have the class file on my class map. So I'm able to do that. Sorry, I got your question. Now, what we're adding into now, if I had this truly distributed, meaning that multiple JVMs, and some of them actually not literally having this class file, this wouldn't work, right? I mean, it would throw a class not found exception. So what we added into JET is distributed class loading as well. So if that class is not there, in addition to sending the serialized function itself, we are also sending the class file as well, distributed class loading as well. That's how we solve that.
So is it doing a dependent class loaded so that anything in return as sort of is in local is also pulled from? But they used to do this
That's
with,
right.
they used to do this with the, they did it for the remote, Java, it was a quick start stuff that basically give it a web space that pulls out the class code from.
You're talking about website.
Yes. Yeah.
Now, I don't exactly know to which extent we are doing that, and there might be some edge cases that it's not going to work, maybe. I mean, this is relatively new, so I mean, you know, but yeah, that's the way we want to solve that. And again, hopefully we did it right. So we need more users, so that's why we understand the edge cases. But yeah, I got the question. Any other question about the topic? Yes.
With what you're doing with Java streams, it would seem like there'd be a very natural fit too for Scala collections. You're looking at that.
So, yeah, Scala. I mean, we haven't done Scala native anything, but yeah, I mean, this is one of the reasons is you can run Java and kind of like in Scala. So we have created for Hazelcast itself. We have created a Scala native API. It wraps a lot of stuff, but also adds a lot more Scala native look and feel, but it's still the same Hazelcast Java API.
And you're not manipulating Scala collections at that point.
We are no. I don't think so.
Well, that would seem like it's just such a natural fit because it's just very similar semantics to what you're doing with streams.
Right.
And in many ways, Scala collections are more established than Java 8 streams.
Makes sense, yeah. Yeah, I guess, I mean, I guess we stick with Java, but yeah, it makes sense.
Stick with Java.
You could have do that to Scala as well. Yeah. Or what you can do is, actually what I was going to show is, the next thing, hopefully we have time to do that, I'm just going to show the code. The underlying API is actually not this one. So technically this is not the JET API. I mean, this is kind of like the wrapper, something that we created on top of JET to make it usable. Because the JET API itself is kind of like really low level. So you don't want any developer to develop it. I'll just show you the code. It's kind of like complex to do even a simple thing. So what you can do is you can take that and then create one for Scala.
Well, that's what I'd be asking you guys to do.
We're open source. There is a reason for being open source, and the reason for me presenting it to you guys, right? Like we literally got a lot of the modules of Hazelcast from community, like Hibernate, Spring, some of the core modules have actually been contributed by the community. So, yeah. But sure, why not? I mean, one day we do that.
Do you have any ways to see, I mean, you gave that example of like where sometimes you're doing something that's remote, or sometimes you change, one line of code and you're actually pulling the whole map back locally. Is there a way to debug that and figure out when am I actually sending it, when am I not sending it? Because you could write that code, it works great on your test environment. You should
Sure, there's no tool for that right now, but yeah, you should. Like
when you called entry set, you suddenly realized it locally.
the reason is because you kind of know. I mean,
No.
this thing over here returns you an IMAP, right? So I mean,
So anytime
if you're not
if you don't have an IMAP, you're in trouble. Right? I mean, it's a way to figure it. You have to stay.
No. Even with IMAP.
Remote.
So what you know is now when you call IMAP.entrySet, you kind of have to know that it's null, it's local at that point, because I mean what you could have done is you could have created another stream, wrap that IMAP, and then do this, right? Then that still would be distributed.
Right.
But I did that on purpose. I mean,
Sure.
I did that on purpose so that I can get this 20 to move to this JVM and print it out there.
Right, but by definition, what comes out of sorted has already had all the different JVMs merged together.
Yes.
And so the limit 20 means you're already local. And so that middle collect set is a
No, up to this point though, you see.
No,
Up to this point.
You cannot sort without doing at least a sort merge.
That's true, but it's not happening on, I mean, of course in this demo everything happens on this JVM, but necessarily it doesn't have to happen on this JVM.
Right, but the limit 20.
Yes, it's somewhere it combines all
has
of
to
them
be
together.
coming
You're right.
local.
Yeah.
And so the sort, what comes out of the sort has to come through the limit, because the limit isn't parallel.
Doesn't have to be local.
Right.
It has to
Right.
resolve somewhere.
No,
It
it's
doesn't have to be
somewhere.
local. Yeah.
No,
it
this
has
is
to be on
local.
your
No,
machine.
but coming out of the 20 by definition has to be here.
Doesn't have to be here, because it could
Not
still be in a
somewhere.
remote map,
No,
which then you
If I-
pull
if
later.
If I say the limit 20 is
Yeah.
collected,
Somebody has to
or do
collect
a
it.
for each, any termination, it's going to be here.
Is limited to
No,
Limit
no,
is
no.
not a terminator, but the
Yeah.
for each is, but
Wait, yeah, that one
but
has
the
to-
limit implies an order,
Yeah.
which basically means the thing before that has to give it a single result.
It has to be one machine, but it doesn't have to be local.
Yes, it goes to one machine.
Right. You said
That's
remote.
right.
It
It
has
goes
be
to
on
one machine.
And the terminator, which is the for each, you could forget about the collect and the entry set, just go right to for each after limit.
Sure, then you pull it.
And the terminator, by definition, has to be on your machine.
That one is-
Now that for each though, the reason I did this locally, because if I don't do that for each trying to run that for each distributed.
Print it on the
But
remote
for
machine.
each is the terminator.
That doesn't, I mean,
Remote,
we
right?
don't say that a terminator needs to happen on this JVM. Then, I mean, like look over here,
So you wrote it to a
right? Nothing
different-
happens on this JVM. We'll already start the stream and we terminate it
You say that
there. But nothing happened on this JVM.
Yeah, why not?
Say it again, please.
You say the for each would happen on the machine?
Yes. If I call for each at this line, that for each lambda will be sent to every machine. like distributed, and for every content each machine has, will be applied there.
Oh, that's a design flaw. I mean, terminators need to come back to where you are.
No, why is, what is wrong with this one?
Well,
So
why
I
do I,
terminated it.
why do I have to turn it into something else just so I can get it back? By definition, a terminator must be on the local block.
You can collect it to map, that will give you what you want.
Except it's not local.
No, then it will.
Well, if you
Map,
use
not
that will
I.
do.
map it by
It's not I, just map. There's lots.
It will convert to a map and give you the map.
It sounds like a great conversation.
Okay. Very quickly, I'll just finish this 3 or 4 slides here. So this is kind of like the way the DAG API will look like. There's a source. You take it, each vertex, you can kind of manipulate. The vertex are computation. So each of these things, I don't have the picture, but imagine each thing is actually happening on every node. So this, of course, source is sharded source, so every node will take their own slice of source. So there was a DAG API as well for that. This is just to show what we are aiming at. Stream a DAG API that's fault tolerant, distributed, focused on stream processing as well. It has these memory management stuff. It can do disk heap, off heap. It can deploy on these guys. Can have different data sources. Interfaces, this is the one interface. DAG API is its own interface. We actually implemented cascading. I don't know if you guys know it. Cascading was the interface for MapReduce and other big data solutions. So we kind of used that as a validation point. That's how the project started. We are looking into having more stream and batch-oriented API that is designed on top of the DAG API, the low-level API. I'm not going to show the low-level right now. Again, it's in a developer preview. So if you're interested, this is the link just to put your name in, or if you're interested in here as well, you can mention that too. We can add it to the preview list. But this is going to be hopefully released before the video, publicly. Not full production ready still, but publicly released. Yeah, thanks. That was all. Yes.
I think of your 2 main direct competitors being Apache Geo from Pivotal and Apache Ignite from GridGame. And so what's interesting about the 2 of them is that in the past year or so, they've both really, really embraced Spark. I remember, I think it was at OSCon last year, I was talking with your co-founder, and I was mentioning this to him, and he was sort of trying to explain to me that he wasn't really envisioning Hazelcast as being sort of that sort of thing. So when I look at this, I sort of see, okay, well, this looks like sort of Hazelcast's alternative to these other guys embracing Spark. So how accurate is that?
I think the way I see it is, once Spark became very popular, there are some, some people rushed to provide some things around the Spark. Eventually we did that as well. One of the 2 customers of ours wanted that. So what we did is ability for Spark to read and write to Hazelcast, to read from and write to Hazelcast. This way, kind of like we can do cache on RTD. Their default cache is local JVM cache. If you want to really good distributed cache, you have, I think it was called Tachyon, and then a little bit name the project. So that's kind of was the alternative to that thing. Not necessarily for Spark community, but also for Hazelcast users. They have data in Hazelcast map, and they want to use Spark, or they have Spark where they're reading from different sources, and the outcome, is ready to serve the public. And Hazelcast, you find it more to be, all TP than OLAP. So, you kind of did everything you did, and the results that is ready, you want to put into Hazelcast where your actually real-time application is reading and, serving to the customer. So, for those reasons, we have that as well. that's kind of what you complement with Spark. And again, whenever something shiny comes out, you'll find a lot of people jumping around that, kind of to ride that wave. We're trying to stay away from that.
But that support is public, part of Hazelcast?
Yeah.
Like
It is
Cache?
it is public.
Okay.
It is public. It is open source, public. Yeah. And actually, if you go to the Hazelcast.org plugins, that's
Okay.
Spark plugin. What this is probably, you could say, more compete with Spark itself, but we don't necessarily think as a compete either, because Spark, Hadoop, they are like from probably much more larger data sets, and they're a little bit more heavyweight. We kind of want this to be, we like to call it Hazelcast style, which is very nimble, simple. You can just embed into your project, have all that stuff within your JVMs. We're very easily not, even though like in the previous diagram I have like ability to deploy this on Mesos and other stuff, but by design, by default, we aim it to be very, very simple. Kind of like all that shiny stuff, Spark stuff, which for all the rest of the developers or everyday developers, kind of like bring that functionality easily to everyone else. By everyone else, I mean like to more use cases. Let's say it that way.
I just want to mention that I've heard a lot of issues recently about Spark having problems, not because of the technology, but because the solutions they've chosen to do are transfer heavy.
Yeah.
And so you spend a whole lot of time getting your data out to the boxes that are going to do the distributed work. And I think one of the key things I'm seeing here is the data starts already distributed.
Yes.
And the idea of, instead of moving it all in and doing the process and just throwing the code out, is I think that's a cool
Yes,
cool
yes,
feature.
exactly. Yeah.
But those are the two main types of distributed systems out there, in terms of distributing the data or distributing the logic.
Had the native Spark support, like in Cassandra, does something similar, but that's with the real persistent story there rather than in memory. Yeah.
So a Hazelcast map question. Do you have a method similar to put it absent where you actually give it a lambda to execute that can fail?
Yes. Let me see. Put if absent. Technically, okay. So let me correct that. So put if absent itself doesn't take lambda, right? It takes, or there's also a replace method where you can provide, old value, the value that you think is going to be there, and new value, and you expect it to replace it atomically, fail or not fail. So yes, so we have that implemented distributed. That's why I mentioned it actually implements concurrent map, not just map. So those are the methods that are part of concurrent map interface. Methods like put if absent, replace. Now, what we also have, now that's not part of Java API, we extended that and we have something called entry processor. So that's where you can send a distributed function onto the entry, based onto the node that has that entry, and apply that function atomically there. So with that, of course, you can do anything. I mean, the sky's the limit, pretty much. Now, that thing is executed on the, we call it partition thread, is just like the concurrent hash map where there's vertices and there's a thread that manages each bucket. The similar concept exists in Hazelcast as well. Now, that thread is the one who is responsible for every update on that partition. Now, we don't want you to hold onto that thread for a long time because any other operation can stall. But as long as you don't do something crazy in there, that gives you the ability to do atomic operations without any synchronization, without any need to do log codes.
My specific goal is to utilize this distributed hash map with optimistic logic.
Yes, you can do that. Yes. Actually, just replace method will do that.
But does replace method handle it when there's no object of there, no value already at all? I've never seen it.
I see. Yeah, maybe. Yeah, you can do that with more entry processor. Yeah, replace. That's right. Kind of like use both sometimes in combination to make it work properly, or yeah, within two processors we can definitely.
Cool.
Well, thank you guys. I guess there's.
I look like that guy right there, but thank you. That was